Assalamualaikum and hi everyone. So we continue on the introduction chapter part 3 for general second order system. Let us now extend the concepts of a poles and zeros and transient response to second order system. Compared to the simplicity of a first order system, a second order system exhibits a wide range of responses that must be analyzed and described. So in this case, we have the second order transfer function omega n squared for the numerator, and for the denominator we have s squared plus 2 zeta omega n s plus omega n squared. Omega n is the natural frequency, which is the frequency of a system after disturbance. Zeta is the damping ratio, is how oscillations in a system decay after disturbance. For example, you are given a transfer function below. We need to find the damping ratio zeta and natural frequency. First, we can find the natural frequency omega n from the numerator, which is this is equal to omega n squared. In this case, your natural frequency omega n is equal to 6. And based on this second part, 4.2s, which is equal to 2 zeta omega n s, so 4.2 is equal to 2 zeta omega n, and our omega n is equal to 6. Okay, so we can determine the zeta using the value of omega n equal to 6, and this equation 4.2 equal to 2 zeta omega n, so our zeta is 0.35. The next one, we also can determine the poles of the system by using the denominator equation through this formula. So the denominator or the characteristic equation equalize to 0, so we can determine the roots or the poles of the system. Otherwise, if we have the value of natural frequency and zeta as in previous example, we can determine the roots or the poles of the system by using this formula. Negative zeta omega n plus minus, you should plus j here because for this case this is complex conjugate poles, omega n zeta squared minus 1. So this is for real part and this is for imaginary part, where you should include j symbol in your roots or your poles. So this is the specification of the homogeneous response from the system's pole location. This is based on the location of your poles or your roots, whether it is complex conjugate on the left side or complex conjugate on the right side, or this is real roots on the real axis. The left side represents a stable region while the right side represents unstable region. To become familiar with the wide range of responses before formalizing our discussion in the next section, we take a look at numerical examples of the second order system responses shown in this figure. So undamped response is a two imaginary poles on the imaginary axis. The natural response is sinusoids. The next one is underdamped response. It has two complex conjugate roots on the left side. The natural response is one which approach a steady state value via transient response, that is damped oscillation, okay, with a small overshoot. The third one is the critically damped response, which has two real equal roots on the left side. Okay, this is two real and equal roots. The natural response are the fastest possible without overshoot. That is characteristic of the undamped response. Okay, undamped response has overshoot, while critically damped without overshoot and has the fastest possible response. And the fourth one is overdamped response, which has two real distinct roots on the left side. The natural response is without overshoot, almost similar to critically damped, but critically damped is faster than overdamped. The step response for the 4 cases of damping discussed in this section are superimposed in this figure. Notice that the critically damped case, okay, this is the critically damped case, is the division between over damped case and under damped case, and is the fastest response without overshoot. Undamped is an oscillatory response. A plot of underdamped response, we are focusing on the second response, underdamped response, appears in this figure for various values of damping ratio zeta, 0.1, 0.2, 0.4, and so on until 0.8. Plotted along a time axis, normalized to the natural frequency. We now see that the relationship between the value of zeta, the damping ratio, and the type of response obtained, the lower the value of damping ratio, the more oscillatory response we have, like this. Okay, the higher the value of zeta, we have more stable region, more stable response. Okay, that's it for part 3. Thank you very much.